This video is about how to work question number 4 from chapter 10-1. So in this question, we're told we have a amino acid, tryptophan, and that it's a diprotic amino acid, and we're given the values of Ka1 and Ka2 there, and we're supposed to determine the pH of each of the following solutions. And so we're given some molarities, some formal concentrations for those solutions. All right, so this is a diprotic acid problem, and there's a nice summary from page 219 of your textbook, and I've copied that here on the right-hand side of the screen. So it kind of divides your problem up into 3 different species, and so you need to think about, well, which species do I have to start with? So they are H2A, so A is just any acid, and the H2 just means that you have 2 protons. So this is a diprotic acid, so it would be the fully protonated form. And we see here that it acts like a, it says number 1 here, treat as a weak monoprotic acid with Ka equal to Ka1. And then we're going to use that to find the H plus concentration, the HA minus concentration, and the HA concentration using our Rice table and plugging into this expression. We can then find the equilibrium H2A concentration by using the K2, the Ka2 equilibrium constant expression, and solving that for A2 minus. And so that's what we would get. And you see here in the simplified form that A2 minus is just equal to the Ka2 dissociation constant. Then if we've got the intermediate form for an amino acid, that would be the Zwitter ionic form. And that's the form that can act as either an acid by donating a proton or a base by taking a proton. And so in this problem, we're going to use the approximation that the equilibrium concentration of HA minus is just the formal concentration. Basically, it doesn't really react that much. And then we're going to find the pH with this fancier equation, or it should be close to, and we can use as an approximate form that the pH is going to be 1/2 pKa1 plus pKa2. So we can use that. And then once we know the H plus and the HA minus concentration, we can solve for H2A and A2 minus using the Ka1 and Ka2 equilibrium constant expressions. And so here they are. And then down here, we've got a solution of A2 minus. So that would be when we have removed both protons. This character acts like a weak monoprotic base. So we call this the fully deprotonated form, and I've called it the base form. And so we're going to treat this as a monoprotic base with Kb equal to Kb1, which is equal to the value of Kw divided by Ka2. We set up our Rice table, and we use that to find the A2 minus, the HA minus, and the H plus concentration using this form. Yep. And then we can use the equilibrium, the Ka1 equilibrium constant to solve for the H2A minus concentration. So in this problem, we're just asked for pHs. So we can stop once we've found the H plus ion concentration in each of these cases. And remember, once we know H plus ion, we can use the fact that pH, so we'll just write this equation up here because it'll be a useful one, that pH is equal to the negative log of the H plus ion concentration, the H plus ion molarity. All right, so we know that that's an approximation because we're ignoring activity coefficients, but this is good enough for our definition here. So we'll use that to calculate pH, and all we need to do in each case is find the H plus ion concentration. Remember that when we solve for X, X is going to be the hydroxide ion concentration for this weak base problem down here. And so we're going to need to do this one extra step to get the H plus molarity. But it's all summarized nicely here in these equations, so we'll be using those. All right, so let's think about what we have in the first part of this problem. So we've got tryptophan hydrochloride, so that's an H2W plus Cl minus. So this is a salt. The Cl minus doesn't affect the pH of the solution. So basically, this is one of those fully protonated acid forms. We've got 2 protons that we could donate. W is our 1-letter symbol for the amino acid tryptophan. So we have these two Kas. All right, so we're working in this form. So we need to use this equation here that says that K1 is equal to x squared over F minus X. Right, so remember, what is X in this problem? X is going to be equal to our hydronium ion concentration, the H plus concentration. So that's what we're looking for. X is also equal to the HA minus concentration, but we weren't told to find that in this problem. Just making a note of that. Okay, so we need to solve for X in this problem. We're going to plug in our numbers, so let's go ahead and do that. Ka1 is 4.3 times 10 to the negative third. That equals x squared over F, which is 0.272 minus X. That's all in the denominator there. And so we just want to solve this for X. So this is kind of on the border of using our small x approximation. Notice that this power is 10 to the minus third. And the power, if we were to write this number in scientific notation with one digit to the left of the decimal point, that would be 10 to the minus 1. I usually like to see a difference of 3 or more in the exponents, and that would be only 10 to the minus 1 versus 10 to the minus 3. That's only a difference of 2 in the exponent. So this is kind of on the edge of being maybe acceptable to do the small x approximation. So I think we're going to use the quadratic approximation in this case. So we just rewrite this equation so that it looks like ax squared plus bx plus c equals 0. And when we do that, we get x squared plus k1x minus f times k1 equals 0. And you can see from this that a is equal to 1, b is equal to k1, and our constant c is equal to negative because of the negative sign right there. Negative, the formal concentration, times the Ka1 acid dissociation constant. Okay, so we're going to plug those numbers into our quadratic equation solver, and I will let you do that. So here's what I get for x. .321 molar, and so now we need to find the pH of this solution. So pH is just going to be the negative log of that number. Which is 2.93. All right, so that should be what our answer is for this first problem, 2.93. So now we've got a 0.272 molar of just tryptophan. So it looks like we've just got one hydrogen here that we can donate. So this must be that intermediate form. All right, we're looking for the H plus concentration, so we need to use this here equation. So H plus concentration is going to be equal to K1 times K2 times F plus K1 times KW over K1 plus F. And then that whole ratio, we take the square root of that whole thing. So we just really need to plug in our numbers here. So we already know K1 is 4.3 times 10 to the negative third times K2, which is 4.7, 10 to the negative 10th. You may have a different amino acid in your problem, but it's going to be worked exactly like this. And then times our formal concentration, which is 0.272 molar. All right, and then we need to add to that. I'm going to go down here so I don't interrupt this white space up here. K1 again, 4.3 times 10 to the negative third times kW, which is 1 times 10 to the negative 14, you'll remember. All right, and then all that, we divide that by K1, 4.3, again, times 10 to the negative third, plus our formal concentration of 0.272. And then the square root of all that mess. So that's not a very straight square root symbol. Sorry for my radical there. All right, so now we're ready to plug and chug, as they say. So let's do that. Plug. And I get an H plus concentration of 2.306 times 10 to the negative 6 moles per liter. So not very much H plus ion concentration. In fact, it's really close to the 10 to the minus 7 that we would get just from water. But that's been included in our calculation, so we're good. So now we just need to find the pH. So we're going to take the negative log of that number. And we should get something, you know, close to 6, right? Between 6 and 7. Or between 6 and 5. So I got a pH of 5.64. 5.64. So this is a very weakly acidic solution. All right, so now we're to the last part of our problem. Let's scroll back up here, see what we got. So we got a 0.272 molar of sodium tryptophanate. So notice that we've got the Na plus and the W minus. There are no hydrogen atoms attached to this. So we can conclude that we've got the A2 minus fully deprotonated or basic form. So we've got to treat this as a weak base problem. And so it says first we need to solve this weak base problem saying that Kb1 is equal to Kw over Ka2. Careful with which Ka you're talking about, Ka2. Why is it this Ka? Because that's the one that involves the conjugate acid-base pair that's in the Kb1 equilibrium reaction. All right, and so that's equal to x squared over, using our formula, F minus x. And remember that x in this case is not the hydronium concentration, but it's the hydroxide ion concentration. So we'll have an extra step where we need to go by and figure out what our H plus ion concentration is. Okay, good. And oh, by the way, it is also equal to our equilibrium HA minus concentration. So that's what you get when you rip a proton off of water. You make HA minus. Okay, so good. We're ready to solve this problem. So let's do plug in our numbers. So Kw is 1 times 10 to the negative 14. Ka2, we saw that from the previous problem, 4.7 times 10 to the negative 10th. And so when I divide those two numbers, that's Kb1. And so that's going to be equal to x squared over F, 0.272 minus x. All that's in the denominator there. And so now we just need to solve this for x. It's probably safe to make the small x approximation, but since I've got it handy up on my computer, I'm just going to go ahead and use the quadratic equation solver here. So same process that we used before. It's going to be a is going to be equal to 1, b is going to be equal to kb1, right, which is this number right here after you've done the division, so this whole thing. And c is going to be negative kb1 times F, our formal concentration. And so you plug all those things in here, that will give you X, which again is the hydroxide ion concentration. So let's go do that. And so I get 0.002395 molar for X. Remember, X is our hydroxide ion concentration. So what we can calculate now is our pOH by taking the negative log of that number. And I got 2.62 for our pOH. Our question was asking for the pH though, so we're going to use our friend that pH plus pOH equals 14, or pKw. It always equals pKw, but pKw is equal to 14 when you're at 25 degrees Celsius. And so we just need to solve this equation for the pH. So that's going to be 14 minus the pOH, and then we just, again, plug and chug. So 14 minus 2.62. And I get a nice basic pH. That's what we were expecting because this is the basic form of 11.38. And so that should be our last pH. And that's how we work problem number 4.